Now that we have studied the forces that drive a protein into the folded state, we want to pay more attention to protein function. To understand protein function, we want to take a look at the reversible binding of ligands. In order to truly understand how a ligand can interact with a protein, we will use the examples of hemoglobin and myoglobin. Both hemoglobin and myoglobin can reversibly bind to oxygen, and they do so in different ways. Let's first think about how a ligand can interact with a protein. When a ligand binds to a protein, it binds to a protein at a very specific binding site. Typically, a ligand is going to bind to its binding site through some sort of transient interaction, such as a hydrogen bond. We will also see some of the other non-covalent interactions that we studied in Chapter 3 and 4 as well. When we think about a ligand binding to a protein, we want to think of this as a reversible and transient process, where when we consider the protein shown here, when binding to some ligand found here, there's going to be a rate of association where we form this protein-ligand complex. When we think of a rate, that's the small k, we want to understand we're thinking about a speed, or how fast and efficient two things are going to interact. Since the binding of this ligand to the protein is a reversible process, we will also have a dissociation rate, or speed at which this protein-ligand complex will dissociate back into an individual ligand and protein. And so if we do a little bit of math, we can actually find an equilibrium constant, just like we would with any other type of interaction, or, we looked at this with ionization reactions, but where the dissociation or equilibrium constant is going to be equal to how fast the protein and ligand can associate divided by how fast the protein ligand can dissociate. So the higher Ka value will tell us that the ligand will more quickly interact with the protein, giving us a higher affinity for the protein. What we typically use more often when we're thinking about protein-ligand interactions is actually thinking about the fraction of occupied binding sites, which is represented by this theta. And now, going through a little bit of math, we can actually come up with ways to calculate theta, where we're looking at the amount of ligand that we have and comparing this to the overall dissociation constant. So a low Kd value, if you'll notice Kd is on the bottom of this equation, the lower the number means we have a higher affinity of a ligand for a protein. Okay? So I think for most students this actually makes a little bit more sense when we look at this graphically. Okay? So what we're looking at graphically here, we're looking at on the bottom, this x-axis, we're looking at concentration of the ligand. So how much of the component do we have that is going to bind to the protein? So of course what we should expect is that as you get more and more ligand, you get more and more occupied binding sites. So remember, this theta represents how many of the protein actually has ligand bound. Okay? So more ligand means you have more ligand bound to protein. Okay? And so as we start looking at this graph, we can look and see that here at this number, this Kd value is going to represent the concentration of the ligand that you need to get to the number of half of your binding sites being bound to ligand. Okay? So this tells me that the steeper my curve here, it takes less ligand to occupy half of my binding sites. So a lower Kd value tells me that I'm going to have a ligand that really likes to be bound to my protein. Where if we have a less steep increase, it's going to take more ligand to bind half of my binding sites. So a higher KD tells me that I need more ligand. So it tells me that the ligand does not bind quite as strongly to my protein. Now, just kind of foreshadowing a little bit, what we'll see with myoglobin, it binds really strongly to oxygen. So we'll have a steeper box here. Okay. Where hemoglobin is not going to bind quite as tight to oxygen, so you're going to have a more spread out curve here. But it is going to get a little bit more complex as we get to hemoglobin, because hemoglobin has a quaternary structure, and so there's going to be some cooperativity that we'll see with the binding. Okay. So let's go ahead and start by looking at myoglobin. With myoglobin, you can see this very, very steep increase. Really, if you have any amount of oxygen, which is the ligand present, you're going to have at least half of the binding sites of myoglobin full, meaning that you're going to have oxygen bound to your protein, your myoglobin. Okay? So no matter how high the pressure of oxygen gets, it's not really making a difference because you have such a strong interaction between the myoglobin and the oxygen. Myoglobin is just always bound to oxygen. And so this is a great thing for myoglobin if we think about the function of myoglobin. Myoglobin's job is to hold on to oxygen in your muscle. And it doesn't need to let go of that oxygen unless you absolutely have no other way to get oxygen to your muscle. So we need myoglobin to hold on to that oxygen very tightly. Now we can also go ahead and start looking at this overall structure that we see for myoglobin, and we'll see this in a little bit more detail in a future slides. Okay? But notice the myoglobin protein is shown here in gray. We have this other structure and shown in red, and then we have something within this red structure. Okay? So this is going to be an extra group that's found within the binding site. Okay? So let's keep digging a little bit further into the structure of myoglobin to see if we can understand how its structure can help with this function. Okay? So a few things to understand about all of the globins, not just myoglobin, but this will be true for hemoglobin as well. We do have the ability to capture an oxygen molecule, and the oxygen is not going to interact directly with the protein. It's going to interact with the heme that is bound to the protein. Okay? And so if we take a look at what's going on with this heme, on all of your globins, including myoglobin, you will have a histidine residue. The histidine residue has a nitrogen that binds to the iron in the center of the heme. And so what I was showing you earlier, this red part represents the heme, and this gold-colored circle, that represents the iron. So by binding this iron directly to the histidine, we block the iron and keep the iron from converting from the +2 to the +3 state. So we block this iron in a state that allows the iron to bind to the oxygen. Okay? So this overall structure of myoglobin is going to have a nice little pocket that the oxygen fits in nicely to interact with this iron. Looking at this a little differently, you can see the larger from the side view structure here. And so the iron actually has one spot at the top and one spot at the top that it can use for binding. So one side is how we're going to bind the iron to the nitrogen of the histidine, and then the other side of the iron is how we're going to bind the oxygen to our heme. Now other things can bind within this binding pocket of myoglobin, but oxygen is going to fit nicely. The oxygen fits nicely so that at the appropriate angle it binds, but it will also let go. Carbon monoxide actually binds even tighter into this binding pocket, but it's not a good thing because it binds so tightly that it will not let go. That's why carbon monoxide is so dangerous. So how do we think about this with looking at the actual three-dimensional, how is the oxygen stabilized within this binding pocket? So again, to orient you, we do have this red, this is our heme, and then histidine found in the F8 region. This is the histidine that is bound to the iron of your heme. Oxygen fits nicely into this binding pocket, and it's stabilized by another histidine residue. So the histidines are crucial to the proper orientation to get oxygen to bind directly into this globin molecule's binding pocket. And notice we do have two other amino acid residues that close off the pocket so that other things don't interact and fit into the pocket. And so now I ask the question, could myoglobin be used for more than storage? Could it be used as a transporter? And so in the lungs, the pressure of oxygen is about 13, so way over here, which would be fine because at the point of the lungs, we want these molecules to grab a hold of any oxygen that we have breathed in for binding purposes. And then we need, when the oxygen gets out into the tissues where the pressure of oxygen is around 4, we need the molecule to release the oxygen. Well, let's find a pressure of 4 on our graph and take a look. Notice here, almost all of the binding sites for myoglobin want to have oxygen bound. So there's no real difference in the binding affinity at 4 versus 13. So at the point of where myoglobin would interact in the tissues, it's not going to let go of the oxygen. So it is not going to be a good transporter. What we need is a graph that would have the ability to not just look this way like we see with myoglobin, but we need to have a molecule that can have a lower affinity state and a higher affinity state. So we need a molecule to carry our oxygen that binds super tight to oxygen when we want it to, but then binds less tightly to oxygen when we want it to. And this is where hemoglobin is going to come into play.